earlier we proved this theorem 5.1.1, and let's actually apply this formula to the following problems. First one is, let's add 3 plus 4 all the way up to 30. That means you are going to add a whole bunch of numbers together, right? You don't really want to manually type these numbers, key in these numbers one on one in your calculator. You want to take advantage of this formula so that you save yourself time. However, this formula starts with 1 and then all the consecutive integers up to n. You're missing 1, 2, 3. This one doesn't start with 1, right? So there are different approaches. The one way that I would do is I'm going to just, how about I add 1 and 2, and then I subtract 1 and subtract 2 so that I can apply the formula to these numbers, right? So therefore I can do that. So therefore you have so you add 1 plus 2, and then you minus 1 and minus 2, and then here from 1 to 70, the n is 70, so therefore it's going to be 70 times 70 plus 1, which is 71, divided by 2. You definitely have to minus 1 and minus 2 again. So whatever this number is, this should be pretty simple to complete. So I'm gonna leave you to complete this one, but here's just show you some ideas. Now for the second one, you have this. We cannot apply the formula directly. The formula is consecutive integers. They're consecutive and starts with 1, right? So we have a lot of numbers missing. However, you recognize these are all even numbers. So one way that you can do is factor out 2, and you're left with 1 plus 2 plus 3 plus, and when the last one will be 50. So when you factor out the 2, this is equal to 2 times, and now you can apply the formula. This time starts with 1 and the n is 50, so it's going to be 50 times 50 plus 1, which is 51, and divide by 2. And you can cancel the 2. This actually is 2550. That's easy to do the arithmetic. And finally, say suppose for h greater than or equal to 2, so at h is any number greater than or equal to 2. Actually greater than 2, I'm sorry, greater than 2. So greater than, strictly greater than 2. Cannot be equal to 2. If it's equal to 2, this h minus 2 is going to be 0, which is less than 1, right? So sorry about that, just strictly greater than 2. Now, it starts with 1 and ends with h minus 2. So therefore your n is h minus 2. You can use h minus 2 times add 1 to the h minus 2. So h minus 2 plus 1 divided by 2. And you get h minus 2 times h minus 1 divided by 2. Okay. All right. Now the next that we want to prove is a geometric series. So what is a geometric sequence? The geometric sequence is, in the sequence, each term is obtained from the preceding one by multiplying a constant factor r. Like for instance, this is a geometric, so for instance, here's the geometric sequence. Say suppose you have 1, and the next one multiply this term by r, which is r, and then the next term will be multiply this r by r, so a constant r, right? So you get r squared. Now you're going to multiply this by r again, you get r cubed, and so on and so forth, and so on and so forth. And say suppose the very last term, suppose it's this guy, multiply by r to the previous one, you get r to the n. Now, so let's add this together, which is 1 plus r squared and up to r to the n. Its summation notation is this guy. If you expand it, this is what you have. We want to prove that this is the result, r to the n plus 1 minus 1 over r minus 1 for all n greater than or equal to 0, okay? Assuming r is not equal to 1. Now, because if r is 1, then this doesn't make sense, right? This is not defined there. So step number one, let's prove the basis step. So the basis step is you have to prove the smallest number when n takes the smallest number. In this case, it's 0. So let's prove that. So the basic step is to prove p of 0 is true, right? In other words, let's check. So p of 0 means this. The left side is n is 0, so you start with 1 plus the very last term should be r to the 0, which is 1, the same as what you begin with, which means you have only one term, right? So p of 0 is the following. 1 equals the right hand side of the p of 0 is when you let n be 0, you have r to the power 1 minus 1, and the bottom is r minus 1. So this is what you need to prove. But isn't that pretty trivial? Because left hand side is 1, the right hand side is also equal to 1. So this is, so p of 0 is this, right? So by the way, prove p of 0 is true, and this is the p of 0. And how do we prove that? You can just say left hand side is equal to 1. Right hand side is equal to r minus 1 over r minus 1, which is also 1. So p of 0 is true because left hand side is equal to right hand side, right? So it's pretty trivial, usually the first step. Now, second step, you're going to assume this formula is true for k, which means you're going to suppose p of k is true. That's what you want to show. That's what you assume. That means, i.e., what are you assuming? What are we assuming? We're assuming this 1 plus r plus up to r to the k is equal to r to the k plus 1 minus 1 over r minus 1. This is what you assume. You don't prove it. You assume this is true. Now, what do you want to show? You want to show that p of k plus 1 is true. That's what you want to show. Now, let's try to interpret this. This means 1 plus r to the k plus r to the k plus 1, right? Because the very n is k plus 1, so you want to make n being k plus 1 equals. Now, the right hand side is r to the k plus 1 plus 1, so r to the k plus 1 and then plus 1 because n is k plus 1 minus 1 over r minus 1, and I usually continue to simplify this a little, so that means r to the k plus 2 minus 1 over r minus 1. Now again, make sure that you are very clear on the flow here. You assume this guy, you want to prove this guy, okay? Now let's begin with the left hand side of what we want to prove. So the left hand side, by the way, when I say left hand side, this is the left hand side of the p of k plus 1 statement, okay? The left hand side is 1 plus r squared plus r to the k plus r to the k plus 1. And you want to take advantage of what you have assumed, and this is what you have assumed. This is equal to r to the k, this is equal to r to the k plus 1 minus 1 divided by r minus 1. This is by supposition to replace these k terms with this ratio plus r to the k plus 1, right? And now I want to do a little algebra so that this is equal to the right hand side of what I want to prove. And again, this is a fraction, so I want to multiply by r minus 1 over r minus 1. So now I have, so now I can actually combine, right? R minus 1 on the bottom. The top I have r to the k plus 1 minus 1 plus. Now, well, let's multiply this, the distributes. these two, so think about distributing these to r and 1, right? So let's expand it. So it's going to be r to the k plus 1 times r, right? Minus r to the k plus 1. Do you see that these two terms are actually equal? They can cancel. So therefore, you have r to the k plus 2 in this case, because this is power 1, k plus 1, add this 1, the power is k plus 2 minus 1 divided by r minus 1. Isn't that this is what we want to show, the right hand side of what we want to show, right? So equals the right hand side, okay? So therefore we can make a conclusion. So therefore 1 plus r to the k is actually equal to r to the we actually use the n there, so r to the n plus 1 minus 1 over r minus 1. So that's another example of using the mathematical induction to prove this result.